In this lesson, we'll see work energy principle. We'll initiate how this came about and give examples of how to compute the work done in a couple of situations. This work energy principle is derived from Newton's second law, which we say as F is equal to ma. Of course, under the assumptions mass m is constant and we are using SI units. So this ma is m dv over dt because a is dv over dt. By chain rule, we say that dv over ds into ds over dt is given by dv over dt, and thus we come about with mv dv over ds. We'll slightly rearrange the terms, that is, we'll take this ds onto the other side and we say f ds is mv dv. We integrate this equation between limits s is equal to s1 to s2. See that s is the integrating variable here, v is the integrating variable here, and so we say that when s is equal to s1, v is equal to v1, when s is equal to s2, v is equal to v2. So this principle, when we integrate between limits s1 to s2 here and v1 to v2 here, is work energy principle. This integral can be evaluated to half m into v2 square minus v1 square. We know that half mv square is the kinetic energy. So this quantity here is change in the kinetic energy. Half mv2 square is the final kinetic energy. Half mv1 square is the initial kinetic energy. So work done is equal to change in kinetic energy is what is termed as work energy principle. And this principle is very useful in solving problems involving force, velocity and distance. Of course, we can use the Newton's second law given over here to solve the problem, but in specific case where the information in the problem pertains to force, velocity and distance, this work energy principle may be used advantageously. We'll try to see this in a bit more detail. Let us consider a particle moving along the same familiar S path, and it is moving from a distance of r1 to r2, a short distance, a short duration of time. It moved from here to here. We take the cause of that movement to be the force F acting on it, that is the force F acting on it caused the particle to move in a short time from position 1 to position 2. And we have seen that very many times we take a convenient point and express the positions as position vectors. So at this instant the position vector is going from here to here, r1 bar, and at this instant the position vector is going from here to here, that is r2 bar. Remember that this r1 bar and r2 bar are vector quantities, though we have not shown the arrows on the head. When it is understood, we often tend to be lazy and omit them. With that understanding, we know from triangle law of addition of vectors, r1 bar plus dr bar is equal to r2 bar. It is a vector addition. Further, we say that theta is the angle between f bar and dr bar as the particle moves from here to here in a short duration of time. Before we go away from this, let me mention here that the time interval between this and this, if it is very short, this dr bar tends to be the tangent to the path at this point. In any case, let us say that dr bar is the displacement r2 bar minus r1 bar, and let us define magnitude of dr bar as ds. Theta is the angle between the tails of f bar and dr bar. Okay. With this notation, the elemental work done is defined as the dot product of the two vectors f bar and dr bar. We know the dot product is defined as product of magnitudes of the vectors multiplied by cos of angle between them, that is magnitude of f bar multiplied by magnitude of dr bar multiplied by cos of theta. Because we defined magnitude of dr bar as ds, this comes out to be f ds cos theta. Because this dot product yields a scalar quantity, we say that work done is a scalar quantity. It may be negative though. In situations where cos theta is negative, work done is negative. One very specific example of cos theta being negative is when the vectors of f and dr, they are opposite to each other. For example, if f bar is going along a positive x-axis and dr bar is going along negative x-axis, or vice versa. In that case, the work done is a negative quantity. Let us see this topic in a bit more detail. Let us say the particle is going along this S path and it is going from S1 to a distance S2. That is, distance S1 is from here to here and S2 is the distance from here all the way up to point S2. At each instant as the particle is going on, it is acted upon by a varying force. That is, the force here may be going at one angle and the force at this instant may be going at another angle. That is, both the magnitude and angle of this force, orientation of the force, may be changing. Another thing that we have already observed in prior example in the previous slide is that at a given point the dr bar, that is the displacement during a very short interval, is tangent to the graph. We have drawn this tangent and resolved the force along that tangent. We will say that the angle between the tangent to the curve and the force as this theta. Now, if we consider a small movement dr bar at this point, we may write that the work done is f bar dot dr bar. This f bar dot dr bar is the elemental work done when the force is acting over a small interval of time and causing the particle to move from here to a very small distance dr bar. And you can integrate between R1 bar and R2 bar. If you want to find the total work done between S and S2, we'll integrate this elemental work done, and which we write as integral S1 to S2 f cos theta ds. Note, if we need to use this integral, we need to obtain f and theta as functions of s, because f cos theta is the integrand, s is the integrating variable. So we need to express this whole integrand as a function of s. This may not be possible mathematically in some situations, but in sometimes we may have experimental data available in the form of a graph between f cos theta and s, in which case you can compute the work done to be the area under this curve. Okay. As an example, we'll see what is the work done by a constant force acting on a particle and moving the particle along a straight line, let us say from distance S1 to distance S2. Because the force is constant, f cos theta is constant, that is what gives this line, and we are moving from S1 to S2, that is what gives this line. And so this curve represents the graph of this area, represents the area under the graph of f cos theta and s, which is f cos theta into s2 minus s1, which we will anyway see mathematically also. Because f cos theta is constant at all the points between s1 and s2, this fc is constant, magnitude is constant, angle is constant, so that we can take out and integrate to obtain the work done by a constant force moving a particle along a straight line, which is inclined to the force at an angle of theta as shown over here. As an example, we'll see what is the work done by a weight as the particle moves along a curved path S from S1 to S2. When S is equal to S1, the radius vector or position vector is R1 from here to here, and similarly it is a vector from here to here, R2 bar. When it is at S is equal to S1, the elevation from XZ plane to the point, that is Y1, is given here. Similarly, the elevation from XZ plane is given to be Y2. Given this setting, we'll try to compute what is the work done by the weight. Note that this P bar, that is the vector representing the weight, is going down, whereas the unit vector J bar is going up. So we say this P bar is minus P J bar, where this P is the magnitude of the vector. And also when the particle moves a short duration, a short length dr bar, we express the dr bar as dx, dy, dz, components along I, j, k directions. Once these two are given, we write the equation for work done. We say that work done from 1 to 2 is integral r1 to r2 p times dr, p dot dr. So this is the dot product. We know that j dot I is 0, j dot j is 1, j dot k is 0. So this work done from 1 to 2 is given as minus p into y2 minus y1. Notice that if this y2 minus y1 is positive, work done is negative. So work done in raising a particle from a lower elevation to a higher elevation is negative. That we note as when y2 is greater than y1, you are raising the elevation of the object. The work done is negative. Work done by the weight on the particle is negative. Similarly, when y2 is less than y1, that is the particle is going down in elevation, work done is positive. As a last case, we will try to see work of a spring force. We will consider a particle attached to a spring whose unstretched position is s is equal to 0, shown over here. That is, at this position the spring is neither compressed nor under any elongation. That is what we call s is equal to 0. That is the first thing we need to observe. Second thing we need to observe is the spring stiffness of a linear spring. Of course, if it's a non-linear spring, you may have a different equation. For a linear spring, the force exerted by the spring is equal to k times s when the elongation is s. So that is the reason why you have the curve of fs and s is shown to be a straight line with a slope of k. So when the spring is elongated by a distance s, the spring force is acting backwards because you are trying to hold this particle and pull it to the right. By Newton's third law, the spring will exert a force in a direction opposite to it. So Fs spring force is opposite to the displacement ds, which is going to the right. Noting this, we will write an expression for elemental work done in moving the particle attached to the spring from a distance of s to s plus ds. Note that s is going from here to here, that is to the right, and the displacement is also going from here to the here, also to the right. We know that force on the particle is Ks because the spring is linear and spring stiffness is K. So Fs is equal to F sub s, that is spring force, is equal to Ks. And because this F and ds are opposite to each other, the elemental work done is negative. That is the reason why you have a negative sign here. So Fs is Ks minus Ks ds. If we integrate between the limits s1 to s2, let us say s1 is somewhere here and s2 is somewhere here. If you integrate this between the limits s1 and s2, you have minus half k into s2 square minus s1 square. Again, note very carefully why we had negative sign. While moving from a point here to here, that is while it is undergoing a displacement ds from here to here, the force is in a direction opposite. That is the reason why we have a negative sign. In the next lesson, we'll try to see a couple of problems on how to compute the work and how to use this work energy principle And so I would encourage you to watch this lesson maybe once or two or three times before you see the next lecture to derive maximum benefit out of this.